We're continuing with solving systems of equations by elimination, but I'm going to put elimination in quotes because I'm going to take a bit of a liberty with this one. We have dx dt plus dy dt equals e to the t, and negative d2x dt2 plus dx dt plus x plus y is equal to 0. The first equation written using differential operator notation is dx plus dy is equal to e to the t. The second equation has our d2x, dt2, dx, dt, and x. And like a lone y term, we can solve for y. And if we do that and express what's left in terms of the differential operator, we find that y is equal to d2 minus d minus 1 acting on x. Knowing what y is in terms of x means we can find dy and plug it into the first equation, which also has x and then the non-homogeneous term on the right-hand side, e to the t. Plugging that into the first equation gives us dx plus d3 minus d2 minus d acting on x is equal to e to the t. We can see that dx and negative dx are going to subtract out. That's going to leave us with d3 minus d2 acting on x is equal to e to the t. The auxiliary equation for that is m cubed minus m squared is equal to 0. That's going to give us m squared times m minus 1 equals 0. And so we have the root m equals 0, which is repeated, and m equals 1. Therefore, x sub c, the complementary function for x, is going to be c1 plus c2t, that's from the repeated root m equals 0, plus c3 e to the t. The right-hand side of the equation we were just working with is e to the t, and so we form our particular solution as it would be a e to the t, except we have some redundancy because one of the solutions to the homogeneous equation is e to the t. And so we have xp is a t e to the t. I'm going to go through the derivatives of xp because it uses a pattern that we've seen, but I think it's good to reinforce it. We have a t and then e to the t, and we're going to use the product rule. And I'm going to think of this as like a t as the first factor, and then e to the t as the second factor. I'm not going to bother with a as a constant that can come out. E to the t is going to show up in every term because it'll show up as itself or as its own derivative. So xp prime is going to be, I'm going to write down some parentheses and then e to the t. And then I'm thinking of a t prime is going to be a times e to the t, and then plus a t times e to the t. And so we have a plus a t. Okay, great. Xp double prime, remember we need the third derivative anyway. Xp double prime is going to be, I'm going to open some set of parentheses here. E to the t is in every term, and now we have, I'll just refer to this as like parentheses times e to the t. We have parentheses prime, which is a, times e to the t, which is outside of here, plus parentheses, which is a plus a t times e to the t, which we already have out here. So xp double prime is 2a plus a t e to the t. Do you want to guess what xp triple prime is going to be? We've got parentheses times e to the t. Parentheses prime is a times e to the t plus parentheses is 2a plus at. We already have an a in here. That's going to be 3a plus at, and then e to the t was out in front of the whole thing. So you can see like it's actually beneficial to see what a pattern would be there. We're going to plug that into d3 minus d2 acting on x equals e to the t. So we have 3a plus at minus the quantity of 2a. So I'll distribute 2a minus at e to the t equals 1 e to the t. Since e to the t is everywhere, I'm not going to write it. At minus at is gone. 3a minus 2a equals 1 is going to give us that a is equal to 1. So x of t is equal to c1 plus c2t plus c3e to the t plus 1. Now we actually have on the screen what y is. Y is the second derivative of x minus the derivative of x minus x. This work is not difficult. I will leave it to you to verify that y of t is going to turn out to be negative c1 minus c2 minus c2t minus c3e to the t minus te to the t plus e to the t. I know, a little tedious. Our next example is a system of three equations with three unknown functions x, y, and z. Equation 1 is dx plus z equals e to the t. Equation 2 is d minus 1 acting on x plus dy plus dz equals 0. Equation 3 is x plus 2y plus dz equals e to the t. If you think back to your algebra experience, if you had a 3x3 system of equations and you were solving by elimination, you would eliminate a variable twice and end up with a 2x2 system. And then that 2x2 system, well, you'd probably eliminate a variable again and end up with one variable. And then you go back substituting and take it from there. And who knows what happens after that. Here we have three equations, but one of them has only two unknown functions, x and z. It seems like it would be judicious to take equations 2 and 3 and eliminate y, thereby getting two equations that have the same two variables. I'm going to ask you to pause this in a moment, but let's, get on the same page here. Here's the plan. Take equations 2 and 3, eliminate y. Let's call the resulting equation 4. Then, take equations 1 and 4 and eliminate z. Just so we're on the same page. Solve for x of t, and then come back and see if we're on the same page. I know that was quite a bit of work. Let's talk our way through it. The plan was to take equations 2 and 3 and eliminate y. We can get that by multiplying equation 2 by 2 and then applying negative d to equation 3. The result is 2d minus 1 acting on x plus 2dy plus 2dz is equal to 0, minus dx minus 2dy minus d2z. And then on the right-hand side, we have the negative derivative of e to the t. That's giving us negative e to the t there. Adding the two equations together gives us a 2d minus 2 minus d acting on x. So that's going to be d minus 2 acting on x. The y's are gone. That's what we wanted. And then negative d2 plus 2d acting on z. Right-hand side is e to the negative t. Our plan was then to take equations 1 and 4 and eliminate z. At least that was my plan. I hope it was yours too. Since I'm eliminating z from equations 1 and 4, we need to apply the d2 minus 2d operator to equation 1 and simply add that to equation 4. Since equation 1 has dx, applying that d2 minus 2d operator is going to give us d3 minus 2d2 acting on x, d2 minus 2d acting on z, that's not a surprise. And then d2 minus 2d e to the t says differentiate e to the t twice and subtract the derivative of e to the t. That boils down to e to the t minus 2e to the t, so that's why we have a negative e to the t here. Equation 4 was unchanged from the previous step here. And when we add together, we get d3 minus 2d2 plus d minus 2, all acting on x. The z's are gone. And then negative e to the t minus e to the t is negative 2e to the t. d3 minus 2d2 plus d minus 2 acting on x gives us the auxiliary equation m cubed minus 2m squared plus m minus 2 equals 0. That nicely factors to m squared plus 1 times m minus 2, and of course we had equals 0. That gives us roots of m equals 2 and m equals plus or minus I. We have the complementary function, but I'm not going to read it because it's in the solution that we end up with. Here we, though, have on the right-hand side negative 2e to the t. Therefore, the particular solution is ae to the t. And you can find by plugging that into d3 minus 2d2 plus d minus 2 that a is equal to 1. Bringing it together, x of t is c1e to the 2t plus c2 cosine of t plus c3 sine of t plus e to the t. And what's the plan now? And it's pretty straightforward, actually. We found what x is. Look at the first equation, dx plus z equals e to the t. If we differentiate x and subtract it from both sides, we get z. So we'll have x and z. And then if you look at equation 3, we can solve for y. So I will note this by giving x into equation 1 gives z. X and z into equation 3 gives y. What that gives us, well, we already had x. Y of t is 3 halves c1 e to the 2t minus c2 cosine t minus c3 sine t. And z is negative 2 c1 e to the 2t plus c2 sine of t plus c3 cosine of t.